Okay, good morning, everyone. All right.
Okay, so Loren Gizon will talk about global scale equatorial Rossby waves in the solar interior. Thank you.
Thank you very much. Thank you for the invitation. Yes, so I will be talking to you about observations only. This is work that was done together with some of my postdocs, Ji-Chao Liang, Björn Luptin, as well as, so Tom Duval also worked on this, and a student, Bastian Proxauf. So what I mean by Rossby waves here are simply waves of radial vorticity that propagate in the retrograde direction. So there has been some work from the late 70s about the existence of these waves in stars. Okay? There's a paper by Papaloiseau and Pringle in 1978 that predicts the existence of these waves. Later, in 1981, the Eigenfunctions were calculated carefully in stellar models by Provo et al. And later, SIO also did some work on this. Some applications for the sun were provided by Wolf, who also calculated radial eigenfunctions. However, these modes had not been observed in the sun until the work that I'm going to talk to you about. And one of the reasons why it was so hard to find them is first that we had no idea where to look, so what spatial scales, what latitudes. But also, this work requires a lot of data, okay, because the periods of these waves are very long. So, but first, a little bit of a reminder regarding the simplest model for these waves. There are a number of key simplifying assumptions that can be applied to simplify the problem. First, uniform rotation at angular velocity, big omega. Usually people ignore the perturbations to the gravitational potential, and so you can actually get solutions for the radial vorticity to be proportional to spherical harmonics, YLM, and the dispersion relation is small omega equals minus 2m big omega over LL plus 1. So yeah, for the period of rotation of the sun is about, say, around 25 days. And so you expect periods for these waves from weeks to several months. Okay. A particular case is the case of sectoral modes, m equals L, and the dispersion relation there is little omega equals minus 2 big omega over m plus 1. Very simple. Okay. So the observations. We use data from these billion-dollar experiments, the ones that Eberhard complained about yesterday. The SOHO spacecraft on the left, SDO spacecraft. First one was launched in 1996, and second one in 2010 with a little bit of overlap between the two. So both of them provide images of the line-of-sight velocity at the surface of the sun that's used for helioseismology. And the SDO-HMI instrument also provides some very high-resolution images of the intensity at the solar photosphere. So in total, we have 21 years of data. We use two different techniques to infer flows, horizontal flows, on the sun and in the sun. The first technique is called local correlation tracking of granulation. So we take these HMI high-resolution images of granulation seen in intensity and look at little patches and see how using a correlation analysis, see how the granules move from one image to the next. Images are separated by 45 seconds, which is much less than the evolution of the pattern. Okay? So you can reconstruct this way the flow field that advects the small granules. Now, the other set of techniques are called local helioseismology techniques, and they use Doppler images as input. So there's a whole set of local techniques. I'm not going to go into these details, but basically we can measure the horizontal component of the flows at various depths in the interior. Okay? And so from these horizontal flows, we can infer the radial vorticity. Okay? So for this first study, which is all based on granulation tracking, the data were actually averaged over a full rotation period. Okay? This is called a synoptic map. So you have the longitude here on the x-axis from 0 to 360, latitude here, minus 50 plus 50, and the colors are telling you about the radial vorticity. Okay? The horizontal flows, here the RMS of the horizontal flows is around 5 meters per second. Okay? So small amplitudes. Okay, so the first question we asked when we got all these maps is how much correlation you have from one rotation period to the next. And if you just look at the correlation without doing anything, you find almost no correlation. I think it was 0.1. Okay. So, that was a bit disappointing first. However, if you only keep the larger scales, in this case less than L of 12, okay, and disregard the smallest special scales, then the correlation increases to a significant number, which is 0.25. If we further restrict the data to plus minus 20 degrees, this correlation goes up to 0.3. Okay? So it's not gigantic, but it is a significant number. And so this was a first hint that was telling us that there is something interesting in the equatorial regions and at the larger scales. Now, of course, the best way to analyze this data properly is to go to Fourier space. So spatially, we do spherical harmonics transforms, and in the time domain, a simple Fourier transform. And so we can construct a spectra, power spectra, of the vertical vorticity and look at those. What's the particular spectrum that's plotted here? So the azimuthal order is on the x-axis here. It's the power spectrum for the sectoral. It's a sectoral power spectrum, meaning L equals M. Okay? And when we do that, we see some excess power in a ridge that follows the dispersion relation that you expect from the Rossby waves. Okay? Now, there's actually, so you see here that the power drops significantly below M of 5 or 6. But if you actually integrate the power in this range from minus 300 to 100 and divide, then you see that this ridge keeps going. Okay? And you see cuts here that are plotted on the right. You have very well-defined peaks that follow this dispersion relation. So for us, this is an unambiguous detection of sectoral Rossby waves. Okay? And so you can see that, a decent fit to the data is a Lorentzian fit. So we can extract a frequency and a lifetime for each of these modes, which are plotted in the next slide. But first, I would like to say that there is no sign of anything in power spectra with M different than L. So you see here the measured frequencies versus the simplest dispersion relation that we have. And really, these numbers are, it's a close match. It's not perfect, okay? So there is some interesting physics probably behind trying to get a better agreement between these two. If we look at the lifetime, the E-folding lifetimes of modes, it can go up to 1 year. One question we had is, why do we see these modes only below about L of 15 or L of 20? Yeah. And so one possible explanation is given here. This is work that we found in this paper here, Wallis and Moltrud, 93. The idea is that there is a transition between a turbulence-dominated regime and a Rossby wave-dominated regime at the Rhine scale, okay, which is the scale at which the typical time scale of turbulence is equal to the period of the Rossby waves. If we put some typical values for the turbulent velocity, here 4 meters per second, this is what we saw in the first map, then we find a Rhine scale of about, with L equals 20. So is this just a coincidence or something interesting to follow up? We'll have to see, but it could be an interesting explanation. Something else we can measure are the horizontal eigenfunctions. Yeah. So if we filter the vorticity around the measured mode frequencies at each latitude, and then correlate this data, between a given latitude and the equator, we find these curves here. So this is for different averages over M, right? Latitude on the x-axis. So what we find are that there is, it seems like there is a switch of sign around latitudes from 20 to 30 degrees. And the values go, a little negative to minus 0.3 maybe, and go back up. So that's not quite as predicted from the simplest model that says that spherical harmonics should be eigenfunctions. And so we tried very hard we tried to see if there was an issue in our analysis, but in the end we couldn't find anything. But there could be a simple explanation for that, which is the fact that we have a latitudinal differential rotation. And if we do a very simple model, a 2D model of Rossby waves in the equatorial beta plane, in the presence of a shear flow, that would represent differential rotation. This shear flow has basically a parabolic profile. And so if we do this work, we find out that it's a singular eigenvalue problem, and we have singular points at the place where the flow is equal to the phase speed. Because these waves are very slow. So they are sensitive to this kind of effects. And so we can get some dispersion relation, which is modified a little bit. And we can also get eigenfunctions like this. And you see that they go negative to minus 0.3, come back up. So, okay, this is only a simple model, but I think if we were to do this in spherical geometry, it would probably work even better. Now, the work I'm showing you now has never been shown anywhere. And this is all about confirming these things with heliosseismology. So we have two techniques, ring diagram analysis and time distance heliosseismology. Ring analysis consists of taking patches on the sun, tracking these patches, and then measuring local frequencies of the P modes. These P modes will be advected by flows, so we can recover the local horizontal flows. So if we, from the UX and UY flows, we construct the vertical vorticity, we can do a power spectrum, and at different depths in the interior. Yeah. This is close to 1 megameter, 1121. And sure enough, if we look at the sectoral power spectra, well, sure enough, I mean, we didn't know at that time, but it actually worked very nicely. We recover the same excess power around this dispersion relation. You see these modes here that you can see very nicely defined here. This is m equals 3, this one. And this is done with, in this case, 6 years of HMI observations. Okay? So that is comforting. The other technique we use is called time-distance seismology. The way it works is that we take 2 points on the surface and correlate these 2 points. So we use the Doppler data and correlate this Doppler data. And from this correlation, we can infer seismic travel times from one point to the other through the interior, and in both directions. So when we take a difference in travel time for waves that go this way and this way, we are sensitive to a flow. In this case, a flow in the theta direction. Yep. Okay. And so we did these measurements around the equator. And for different travel distances, okay, ranging from a few degrees to 30 degrees. The bigger the travel distance, the deeper you can go in. And then we averaged all these travel, the seismic travel times over these distances by weighting the data so that we have the best signal-to-noise ratio. Overall, it corresponds to a mean travel distance of about 15 degrees. And so a depth of 0.9 radius, solar radius. So why do we care about U theta, by the way? That's because if you have a mode like this, a Rossby wave or mode like this, then you see that along the equator, you will have U theta that goes plus, minus, etc. Yeah, thanks. Okay, so that's why we are looking at U theta. And by this time, it's seismology, so we can use all of SOHO data. Yeah? So we can add another, basically 14 years of data. Okay? And so you have the seismic travel times on the left here. This is the longitude in the co-rotating frame on the x-axis, and time. Yeah. So the data are just piled up here. Of course, we don't have full coverage because we see only half of the sun, but that's life. And these are power spectra for the first 7 years of data, next 7 years, and last 7 years. Okay? The first two is mostly SOHO data, and last one SDO data. And you can see that we have this excess power again along this dispersion relation. It's not as clear as the vorticity measurements that I showed before, but the signal is there. And then when we combine 21 years, there's no doubt that there is mode here, boom, 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 okay? So it's a nice power spectrum, 21 years of data. These are cuts through the power spectrum at different M values. M equals 3, 4, 5, 6, 7, 8, 9, 10, 11, and it could keep going. So you see that some modes are very nicely defined, like M equals 3, the long lifetime equals 5, 7, 8, these are nice. Some are a bit more messy. M equals 6 is a bit messy. Maybe M equals 4, I don't know. And then the lifetime goes down for bigger values of M. Okay, the green line is from the simple dispersion relation. Yeah? So for values around 6, 7, 8, this is really right on. But for M equals 3, it's shifted. M equals 4, a little bit shifted. Okay. This I will skip. We asked the question about the radial eigenfunctions also. Yeah? So instead of averaging over the distances, travel distances, we can actually focus at different depths by considering different sets of travel distances. And this is called deep focusing. So we measure travel times in the u theta direction, for u theta, calculated power spectra, look at the amplitude of a particular mode, it's at m equals 8 for different focus depths. And we get a decreasing function. So, and then what we did next is to consider a model that's provided by Provo in 1981 of an eigenfunction for a Rossby mode under the assumption that we are in a marginally stable stellar interior. Okay? So in between the radiative zone and convection zone. And the answer is just r to the m. Right? So we can take this and do a forward calculation. We put r to the m, do some ray calculations, and predict the travel time that would be given by this depth dependence. And it seems like it's a pretty good match, actually. Okay, so it's an interesting measurement. But we obviously need to go deeper. Here, it's a little analysis that shows, we can just look on the right-hand side, that the amount of power that is in the Rossby waves compared to the power that's outside of the Rossby wave is almost the same for modes around 6 to 12. Okay? So there is really a lot of the vorticity power, it's vorticity power, a lot of the vorticity power is in the form of Rossby waves at these very large scales. This one is for the surface. Yeah. Right. The last really piece of interesting information is the amplitude of these modes as a function of time. We have 21 years, so we can look at the amplitude of the peak, or the power in the peak, as a function of time. Okay? We can do this either with a moving time window, or to do a wavelet analysis. And so this is quite interesting, but we haven't had time to really look into the details of this. I just show you the results that were obtained just some days ago. You have, so for example, if we take m equals 6, we see that the power in this mode is going up and down. If we plot next to it the sunspot number, it's not so unlike the sunspot number. So don't know what it means, but it's one piece of information. Quite a few other modes seem to have higher power when the activity is highest. However, the m equals 3 mode is different. This is the opposite. It has more power during the quiet times. That's what you see here. So it's first 7 years, next. For m equals 3, there's a big peak here in the second panel, but there's nothing basically before and after. Okay, so summary, in the co-rotating frame, and more precisely in the frame that co-rotates at the equatorial rotation rate, this is what we see. Oops. This is supposed to be a movie. Yes. Okay, so these are 3 example modes, 3, 7, 11. They have frequencies of minus omega over 2, minus omega over 4, minus omega over 6. And the eigenfunctions are not spherical harmonics. There's a switch of sign here. So I think we have a clear detection. We see these modes both in MDI and HMI data, and we've looked at 3 independent methods. The dispersion relation is not far from the classical, I would say, dispersion relation, although it's not quite perfect, so there would be some work to be done here. The eigenfunctions are not quite spherical harmonics, probably due to latitudinal differential rotation. The modes persist down to at least 100 megameters, at least for this m equals 8 mode that we looked at. And we think that these Rossby waves are definitely an important component of the large-scale solar dynamics. Now we see no connection whatsoever actually with there was some work done by Scott McIntosh in the corona of moving magnetic patterns. However, these have the opposite phase and group velocities, so it can't be related. Future work will have to, I think an interesting topic is the study of excitation and damping of these modes by convection. The connection to solar activity is certainly interesting. We want to push the helioseismic analysis deeper and look in numerical simulations if we can see these modes. Of course, the big question is, what role do these waves play in the overall global dynamics of the sun? We don't know. Maybe somebody knows, but we don't know. And there may be applications of this work actually in particular to the evolution of exoplanetary systems via star-planet tidal interactions. Because in this topic, the lifetime of the inertial waves is very important in deciding how easy it is to transfer angular momentum from a planet to a star. So that could be interesting. Okay. That's it.
Very nice results, Laurent. I was wondering if you use the individual M's, if you see a difference in the rotation rate, actually, since the different M's are sampling different parts of the flow of the differential rotation, then maybe you can.
Right. So. Yeah, so that could be part of the explanation why the match to this dispersion relation, the simplest one, is not perfect. This is the kind of thing we have to look at. But yes, there should be a little effect like this. Yeah.
I guess probably related to the not perfect dispersion relation again. It looked like above m equals 15. The power ridge was above the model dispersion relation. Do you have any comment on that?
Sorry, could you please repeat?
There looked like to excess power, the form of the relationship was above the model dispersion relation.
Yes.
M greater than 15.
I would have to see. Yeah, I see what you mean. We can't
Most
really
clearly in the
here.
earlier ones, but.
Yeah, but the thing is that as we reach M values around, say, between 15 and 20, we can't really identify these modes anymore, because when you look in kx, ky space, you see power, isotropic power, right? So you're kind of looking at turbulence again. There's kind of a transition there, so that's also why we don't really plot the mode frequencies beyond 15. No.
You did have them in your first plot when you were using the correlation analysis.
Maybe. Okay, yeah. Yeah, so this stuff here can definitely not be identified as Rossby waves. Okay? This is around zero frequency. And if you were to look in k omega space again, kx, ky space, you have power in all directions. Also, yeah. So I would say this is convection or turbulent convection. These are waves, and in between there's some transition.
Just comment to this question. Actually, this m equals 11 or 12, which is the excess power, corresponds to the observed oscillation in solar activity like Rieger type periodicity, which is around 5 months.
11, sorry?
Observed in the solar activity 5 months periodicity as a Rieger type. So maybe this is because of coincidence.
I mean, this is really around zero here.
No, I mean m equals 11, 12, which has a maximum power, right?
Yeah?
Yeah, this one. Quite
okay, I don't know. Yeah.
And also, important point is that this Rieger periodicity has appears in maximum, like you showed. I think it's very, very
So,
interesting.
so you're saying that, I mean, just to try to understand, the Rossby wave could have something to do with the Riga periodicities?
Yeah, yeah.
Okay.
Yeah, there are papers about this, so I think it has quite good connection.
Mm-hmm.
So what is the velocity amplitude of these Rossby waves compared to the giant cell convection you measure? It's
So-
consistently as
So
low as
each
that.
mode is probably below a meter per second. Right.
So it's similar to the low amplitude of giant cell convection velocity you measure.
So giant cell convection,
I mean, you put an upper limit on that. Similar.
we haven't really studied this. Maybe you're talking about,
You know,
what M values are you talking about?
610 something.
610, where we see nothing there. So,
I mean, okay. meters per second, you're saying.
yeah, but we don't see those. I mean, they don't seem to be in that power spectrum, at least.
So, excuse me, the simple dispersion relation that you've put
Yeah.
up, I haven't seen its derivation, but you can immediately notice it doesn't have any information about the stratification of the sun. Is it expected that if you did a more full treatment, that there would be effects having to do with stratification?
That's correct. So if you read the paper by Provost et al. 1981, where there's a detailed analysis of this, it says that it's really important to have to put the full structure in, have a convection zone, a radiative zone, and actually in the work by Wolf, he says that these modes should be even trapped in the convection zone. They can't go below the convection zone. So the structure has an effect, yes.
Which M values are most likely to be affected?
Right. So if you look, for example, at m equals 8, something that goes like r to the 8 would basically die at the bottom of the convection zone. So maybe it doesn't fill the bottom of the convection zone. If you go to m that are smaller than that, I think this r to the m will not be correct. But yeah, it's work to be done on this.
Maybe this is just a question of semantics, but when I think of a Rossby wave, I think of something that has a frequency that is very much smaller than the background rotation frequency of the body. But you're talking about waves that have frequencies on the order of the rotation period, is that right?
They just, yeah, I mean, they're below 2 omega, right?
Okay.
That's, sure, I think that's pretty standard, but.
Okay. Okay, I have one final question. So your waves go in a different direction to Scott McIntosh's, and his are presumably magnetic Rossby waves. So can you?
Not on purpose. I mean,
can you use
I respect Scott.
Can you? Yeah, you have to say that, don't you? Can you use these results, or could one use these results to place constraints on the size of the magnetic field? Because magnetic Rossby waves might want to go a different way.
I have no idea. We haven't studied any of this.
Yeah, sure.
In this scenario, it's purely hydrodynamic, what Roland showed. Then this mode is split into fast and slow mode. So it's possible that the one corresponds to fast and another to slow. So they propagate in. Yeah.
Absolutely, yeah. And the magnetic field can make them go in a different direction.
Exactly.
Yeah. Okay. Let's thank Laurent again.
Thank you.
Okay, so we have a change to the program because Lee is unfortunately not well. So he's going to speak, hopefully, the last talk tomorrow. So instead, we have Federico. Okay, so you're using your own computer. So I'll tell you when you've got 10 minutes and then 5 minutes to questions. Mm-hmm. Okay, and Federico is going to tell us about a whole atmospheric perspective on connections between intraseasonal variations in the troposphere and thermosphere.
Well, I'd like to start by thanking the organizers for inviting me here. And I realized that some of the material in this presentation may be less familiar to you, so we'll cover some of the background information as well. But yes, the title of my presentation is a whole atmospheric perspective on connections between interseasonal variations in the troposphere and thermosphere. I'd like to acknowledge the contribution from my postdoctoral mentor here at HAO, Han-Li Lu. And in this presentation, I'll present results that will take both the advantage of the satellite perspective. In particular, I'll demonstrate satellite observations or results that use satellite observations from the timed Gocha and Champ satellites, but also numerical models developed here at HAO, such as the timed DCM and Wacom X 2.0. So as an overview of my presentation, as I said, I'll cover some of the background information. Then I'll describe the data, models, and methods that I've used. And then I'll spend quite a bit of time describing the main results that I'd like to show here today, which are evidence of tropospheric 90-day oscillations in the thermosphere, and then wrap up with the conclusions and summary. So starting with the background, here I'm showing you the different layers of Earth's atmosphere. We have the troposphere, stratosphere, mesosphere, and the thermosphere higher up than 85 kilometers. Essentially, in terms of energy sources in the thermosphere, which is the focus of the region that I focused primarily, we have energy sources from above, in particular the absorption of solar UV radiation, but also high latitude processes such as joule heating and particle precipitation. But really, in the last decade or two, evidence has demonstrated that dissipation and energy momentum deposition from upward propagating waves that have been generated in the lower and middle atmosphere are really affecting significantly the variability of the both thermospheric and ionospheric systems. So to better show this, I'm showing you here an illustration from the Solar and Space Physics, the Decadal Survey, which shows you here in green the lower atmosphere, and in gray we have the ionosphere and thermosphere. So there is a group of waves that I'll describe in further detail on the next slide that have different spatial and temporal scales. We have the gravity waves, planetary waves, and tides. A subgroup of these waves is capable of propagating upwards in an exponentially decreasing density. And so their amplitudes may be very small down here, but they do grow in amplitude, and those that are capable of propagating all the way up to the lower thermosphere and above are capable of imparting significant variability into the thermospheric system through dissipation and breaking, but also can couple into the ionosphere either in the E region or in the F region. So what waves are there? Well, before I get into there, as I wrote here, the primary mechanism through which energy and momentum are transferred from the lower atmosphere up to the upper atmosphere and ionosphere is through the propagation of waves. So to briefly describe them, gravity waves are those that have somewhat small temporal and spatial scales, and they're primarily excited by orographic instabilities, and they are capable of propagating all the way up to the thermosphere. Then we have Rossby planetary waves, and there has been some discussion on those here before. Those do not propagate easily to the thermosphere and have time scales up to or over a month. Then we have solar tides, and I'll describe this in the next slide, so I won't spend any time here discussing them. And then we have Kelvin waves that are also propagating up to the thermosphere, and that I'll also describe in the next couple of slides. So this, jumping to discussion for tides, these are primarily excited by the periodic heating of the atmosphere by the sun, but also by tropospheric convection, in particular in the tropics. And so you can imagine that the heating from the sun excites a spectrum of tides, but the heating occurs in the troposphere by the absorption of infrared radiation by water vapor, and higher up in the mesosphere by absorption of ultraviolet radiation by ozone, and higher up in the thermosphere by molecular and atomic oxygen. So the heating rate can be imagined to be essentially schematically the following, where we have essentially no heating during the night and only heating during the day. And the heating rate can be decomposed in a mean component, a diurnal component, so a 24-hour period, semi-diurnal component. And you can imagine that the heating occurs in different regions of Earth's atmosphere, and that generates a spectrum of tides that are described generally by a summation of cosines, where the frequency of the tide is n omega, and this parameter here, S, is the so-called zonal wave number, and that describes the longitudinal dependence of the tide, and it is assumed to be positive to the west in this notation. And you see that the summation here depends on the has the summation of cosines has an amplitude that is a function of z, height, and theta, which is latitude. Also, it's a summation of different tidal components that have, for the interest of upper atmospheric studies, we usually consider zonal numbers of plus or minus 5. So the speed at which a tide moves in the east-west direction is the zonal phase speed, and that's equal to n omega over s. So for those tides that have s equal to n, those are referred to as migrating tides, and the tides that have s different than n are referred to as non-migrating tides. And in the last probably 2 decades or so, a lot of studies have shown the importance of non-migrating tides in generating variability in the upper atmosphere, whereas initially only migrating tides were accounted for in some of the modeling or some of the models developed. On a fixed local time frame, the previous expression up here becomes the following, where you see the only difference really is in the longitudinal dependency. So it's no longer dependent only on S, the zonal wave number, but S minus N. So essentially, migrating tides are not resolved in a sun-synchronous fixed local time frame. And I'll describe some of that in the later part of my talk. So in the standard nomenclature for tidal, in the tidal theory, DWX and DEX denote a westward or eastward propagating diurnal tide that has a zonal wave number x equal to s. So for semi-diurnal and true-diurnal tides, S and T replaces D. And so an example of that is the so-called DE3. That's the diurnal eastward propagating tide that has zonal wave number -3. It has been shown to be a very large and important source of variability in the thermosphere and ionosphere. It is primarily excited by tropospheric convection, and its first symmetric mode is a Kelvin wave that has basically no meridional speed. And I reported the D3 here in this slide because I'll show some examples of this tide that, as I said, is primarily excited by tropospheric convection. So Kelvin waves are also global scale waves that are similar to D3, primarily excited by tropospheric convection, and they're primarily, as I reported here, equatorially trapped, and they play an important role in coupling the lower atmosphere with the upper atmosphere. And they're generally grouped in 3 different classes. We have slow Kelvin waves that have periods of 10 to 20 days, then fast Kelvin waves with periods up to 10 days, and the so-called ultra-fast Kelvin waves that have periods of 2 to 6 days. And only those are the ones capable of propagating up to the thermosphere. And I'll demonstrate some of the results of these waves. So jump into the data and models and methods that I've used. I used data from the timed satellite, in particular the SABRE instrument. This is a NASA mission that was launched in the later part of 2000, and it's still operating. It has provided very valuable measurements of the thermosphere and ionosphere. But SABRE is an instrument on board the TIME satellite that it's a limb view instrument that provides temperature estimates between 20 and 120 kilometers, and it has a local time precession period of 120 days or so. And then we have I've also used the data from the CHAMP satellite. This is a German satellite that was launched in 2000 and re-entered in 2010. And it had on board a very accurate accelerometer that provided estimates of neutral densities and cross-track winds. So the so-called the cross-track winds are the winds in the east-west direction to the direction of motion of the satellite. CHAMP has a local time precession period, or had a local time precession period of 260 days. And the reason why I report the local time here is because that's relevant to decouple certain tidal components and has importance that I'll later describe. Then we have the data from the GOCE satellite. This is a European ESA mission that was launched in 2000 and re-entered in 2013. Similarly to CHAMP, I've analyzed neutral densities and cross-track winds, and GOCE followed a sun-synchronous dawn and dusk orbit. Then I've also looked at OLR data. This is outgoing long-wave radiation data measured by NOAA and NASA satellites that provides a good proxy for tropospheric convection, and that's the reason why I've analyzed this. And I'll demonstrate some results that take advantage of OLR measurements. In addition to satellite observations, I've also used modeling analysis. In particular, I used the TIME GCM. This is the thermosphere, ionosphere, mesosphere electrodynamics general circulation model. It's a model that has been developed here at HAO, and it is a different version of the more commonly used TAE GCM, but it also incorporates the mesosphere. That's what the M here stands for. The model simulation was run between the years 2009 and the early part of 2010. And the boundaries of the models are 30 kilometers to 500 kilometers. And the lower boundary in particular is set using MERA data. And I'll describe this later, what MERA is. But important to note is that that provides a good estimate of what the wave spectrum looks like at the lower boundary of the model. In addition to the TIME GCM simulation, I've also analyzed WACA-MAX modeling results. This is the whole atmospheric community climate model with the ionosphere and thermosphere extension that also has been developed here from HAO. The 2.0 version is the current version. There is a release coming up, I think, later this month with the 2.1. But important to note is that the lower boundary for the simulation that I've analyzed has specified dynamics. So MERA-2 data is used as a simulator in the model between the surface and approximately 60 kilometers. And in addition, I've also analyzed MERA-2 data, which is used at the lower boundaries of these models. This is a NASA reanalysis physics-based weather prediction model and provides good estimates of various geophysical fields dating all the way back to the 80s. So in terms of some of the methods that I've used, here I'm showing you a plot of S10.7 in magenta up here and AP, 3 hourly AP values in green for a 15-day period that I've analyzed. So essentially, to minimize the effect due to solar and geomagnetic activity in the thermospheric GOCE data, I fit the GOCE data in 15-day running windows to the F10.7 or S10.7 and AP. S10.7 is a different proxy for UV radiation. It's a different version of the more commonly used F10.7. But you see here, the fit really is able to capture some of the variability in the thermospheric data. But anyways, I removed those fits from the raw data so that I can better concentrate on the wave signals. One of the issues in extracting different tidal components from satellite measurements is that we would have to have all local times, and the problem is that essentially to have all local times in solely processing orbiting satellites, we have to average over several days, and so we are not able to capture the day-to-day variability in the different tides. So to overcome that issue, I used the so-called ascending minus descending method. So we can write an expression for a tidal component, the ascending node, and the descending node in the manner reported up here, where essentially then we take advantage of the fact that the difference in local time between the ascending node and the descending node of this polar orbiting satellites is approximately 12 hours, to simplify that expression to the following, where essentially we can fit wave S minus n into the ascending minus descending divided by 2 residuals, and obtain the amplitude and phase of the diurnal tide. Essentially, using this method, we are able to decouple between or to separate the semidiurnal with the diurnal tide, and but also it introduces some issues, such as we're not able to distinguish waves that have the same S minus n, nor we're able to distinguish migrating tides because of that. Jumping now into some of the results, here I'm showing the daily D3 tidal amplitudes from the SABRE instrument around 110 kilometers. So you see that D3 has a lot of day-to-day variability in a latitude versus time frame for the 3-year period that I've analyzed. You see that D3 tends to maximize in the later part of the year, in particular in the after summer months. Really my contribution here was to demonstrate that the Gauche data at 260 kilometers also had a similar variability. And we're looking at here 20 Kelvin down here at 110 kilometers and 8% variability over the background in the Gauche data. So essentially in this study, I was able to demonstrate that there was propagation of this tidal component between the lower and middle thermosphere. Looking then at the same data set, the time SABRE data at 110 kilometers, I was also able to detect and extract the amplitude of the ultra-fast cam wave at 110, but also 260 kilometers. So similar to D3, I was able to demonstrate that this wave is capable of propagating from the lower to the middle thermosphere. And now in addition to this, in a different study, I analyzed the effect of the mean winds, and I heard some discussion in some of the previous sessions yesterday and the day before on the effect of mean winds on tidal propagation. And so here I'm showing you D3 and the ultra-fast scan wave in the time GCM model. You see the amplitude and the height versus latitude frame. You see that the D3 tends to maximize in the southern hemisphere in this particular period of time, and the ultra-fast cam wave also has a significant latitudinal asymmetry. K1 and K2 are secondary waves that have been generated by the nonlinear interaction between these 2 primary waves. I won't have time to describe these in further detail, but you can refer to my paper for details. But really, the importance here is that in this paper, I was able to demonstrate that the zonal winds play a very significant role in the vertical propagation. In particular, these waves that are eastward propagating tend to propagate in westward winds. And the reason of that is because of Doppler shifting that occurs. So essentially, in eastward propagating waves that are propagating in a westward wind are Doppler shifted to higher frequencies, and therefore are less subject to dissipation. In the same study, I was also able to demonstrate that the latitudinal broadening with height was mainly dependent on the effect of dissipation. Here, what I'd like to discuss is something new that I found somewhat recently, later last year, published in GRL, which is evidence of 90-day oscillations in the thermosphere. So here I'm showing you a CHAMP zonal winds around 330 kilometers in a period versus time. So this is a wavelet plot, and CHAMP D3 is on the right. So you see that there is a very strong 90-day oscillation in the CHAMP data. If we're then looking at the Gauche data for a similar period of time, we also see a significant 90-day oscillation. And if we then look at the time GCM simulation for the same period, also that exhibits a similar 90-day oscillation. Now the question is the 90-day oscillation in the thermospheric winds connected to geomagnetic or solar effects? And so for that, I've looked at AP and F10.7, which don't exhibit any sort of 90-day oscillation. So where is the oscillation really coming from? That is a question that I've tried to address using some of the models. So here I'm showing you the time GCM zonal mean winds in a height versus time profile, and the three tidal amplitudes. So you immediately notice this variation here that's the semi-annual variation, but you can also notice what looks like a 90-day oscillation in the thermosphere. So to better analyze that, I filtered the data using an 85 to 95 day bandpass filter, and you see that the oscillation is very strong with amplitudes over 20 meters per second in the winds and 3 meters per second in D3. Really the important connection that I made in the same study was to analyze OLR data in the troposphere. This is a line plot in blue here of OLR around the equator, average, I believe, plus or minus 30 degrees, which also shows a very significant 90-day oscillation in it. And time GCM, of course, shows the 90-day oscillation that I previously described. So then taking a bandpass filtered version of those data sets, which I'm showing here, OLR in blue again, time GCM in winds is in red, I was able to find a correlation between the zonal winds and OLR. And here important to note is that we are comparing something in the troposphere with something higher up in the thermosphere. So in addition to that, I was able to also detect some phase relationship between the time GCM, thermospheric winds, and OLR. But more recently, and in some published work, still looking at the lower boundary, looking at MERA2 zonal mean winds at 30 kilometers. So you see here for the year 2009, what you're looking at latitude versus time, you see that in the winds, you see that wind structure here that's due to the southern stratospheric warming event that happened later in January 2009. But you also see a bandpass filter version of the MERA data, and you see that there is a 90-day oscillation in it in the first part of the year and the second part of the year, with amplitudes of plus or minus 20 meters per second that are somewhat large compared to the overall variability. And also the other thing that I like to point out here is that that oscillation tends to be concentrated in the troposphere around 70 degrees or so in latitude. So if we're looking at a global plot of MERA2 zonal winds around 30 kilometers for the entire year 2009, you see that the oscillation tends to concentrate around the polar jet region, and another view of that is provided here, where you see that the amplitude maximizes between 60 and 80 degrees in latitude. And it also has amplitudes of 19 meters per second. So if we then look at the WACAM-X data at around 31 kilometers or so, you're basically looking at also very similarly to MERA data, because that's assimilated in the model around 30 kilometers. You see here for plus or minus 90 degrees in latitude that if we take a bandpass filter version of the raw data, that the oscillation concentrates around the polar region, so really around 70 degrees or so. But it's not only concentrated around 2009 and 2010, but in for different years as well. In fact, the round was performed between the year 2000 and 2015. And it is of interest, of course, to further see if there is a connection to perhaps the ENSO and any stratospheric warming events. But I'd also like to point out that the amplitudes are very large in the polar regions, so that's something important to point out. So in conclusion, I've analyzed Champ and Goche cross-track winds to reveal the existence of a strong 90-day variation in the thermospheric mean winds with amplitudes of plus or minus 20 meters per second, and D3 tidal amplitudes with amplitudes of 3 meters per second or so during 2009 and 2010. Modeling results, in particular time GCM, WACAMAX 2.0, and MERA2, demonstrate that this oscillation is also present in the lower and middle atmosphere, and is not really propagating from below as a wave. In fact, I didn't have time to show this, but it has this oscillation doesn't have any vertical phase progression, so it's not a planetary wave that is propagating from below. Analysis of OLR data reveals that the oscillation is present also in tropospheric convection, and that it correlates with observed and modeled thermospheric winds. Preliminary analysis of MERA2 data indicates that the tropospheric 90-day oscillation may be connected to the northern hemispheric polar jets. That's something that I've worked and that I'm working on right now. And that it's not only limited in 2009 and 2010, but it also occurs during other years. So our results suggest that tides and gravity waves are probably modulated by tropospheric convection at a period of around 90 days in the lower atmosphere, and as these waves are propagating and dissipating in the thermosphere, they're imparting or imprinting this oscillation into the mean thermosphere. But of course, a lot of work has to be done to really assert that for certain. But my study really demonstrates that there is a significant coupling between the lower and the upper atmosphere on intraseasonal timescales. And as I said, that a lot of work has to be done to really understand what the importance is of waves in this coupling. With that, I'd like to thank you, and if there are any questions.
Could you estimate from your results how much power is then being dumped into these high parts of the atmosphere? And how significant is that compared to, say, UV deposition?
Right, so that's something that I'm working on specifically for the 90-day oscillation in terms of estimating what the overall power is. But if you're looking at the overall variability over the background, waves can really some studies have shown that these upper propagating waves are capable of generating over 35% of the overall variability and 40%. In one of my previous papers, over a very quiet, geometrically low and period of time, I was able to demonstrate that the overall variability due to waves was up to 50% over the background. In terms of estimating the power, I'm sure some previous studies have done that, but I'm not really familiar with that.
Can you connect any of the modes, particularly the 2009-10 that you showed, to some of the oscillations that we saw this morning? Particularly, that was, I believe, ENSO year. There's any connection to that?
Could you repeat part of the question? I think I missed the first part.
Can you connect the observational evidence that you saw to some of the modes that we saw this morning?
Right. So I think finding a connection between ENSO and perhaps just a 90-day oscillation would be something very important to look at. In fact, since the WACAMAX simulation was run all the way for 15 years, from 2000 and 2015, looking at a potential connection to the El Niño Southern Oscillation is something that I would want to look at. But presently, I don't have any input on that.
Okay, our next speaker and the last speaker of the session will be Susan Horn from UCLA. She'll be talking about flow morphologies in low parental number rotating magneto convection.
Okay, so hello everyone. Oops. So I want to talk about a rather idealized system of rotating magnetoconvection, and that means I look at a cylindrical container which is heated from below, cooled from above, and I'm applying an external magnetic field. And the thing that's really special here is that I'm looking at a low Prandtl number fluid, and that means I'm looking at a Prandtl number of 0.025, which corresponds to a liquid metal. And I want to show you that this is rather different to what we have seen here in most of the talks, namely using a Prandtl number of 1. And I first kind of want to motivate why we care about a cylinder in particular and why I'm not using a sphere. And then also explain why I'm using a very simplified model of a quasi-static approximation, and then revisit some ideas of Chandrasekhar. So we have done several studies in combination with with laboratory experiments at UCLA, where we have a cylinder. And for low Prandtl number fluids or liquid metal, even if we have just a normal Rayleigh-Bénard system without rotation, without magnetic fields or anything, we were able to find something really new. And for example, the large-scale circulation here behaves rather differently. It's not just a normal circulation, but it behaves more like a jump rope vortex. What's very important too is that if we have rotating convection, we don't have these typical stationary columns, but instead we have oscillatory convection and a very multimodal flow. And this is one example of a liquid metal simulation. And what we see is this is temperature mode and this is an azimuthal mode. Here we have some nice torsional oscillations. And another point that's important, so I've heard it several times that oscillatory convection is not really important because it's just oscillating. It's not very efficient in transporting heat. However, what is important is it's extremely efficient in transporting momentum. And here are some measurements from Tobias Vogt done at UCLA. And this is very close to onset, so the critical supercriticality is only 3.6, and yet the velocities that can be reached are about 20% of free fall velocity. Right. So the whole reason why we do cylinders is, of course, we have ROMAC at UCLA, which is a cylinder, and it's kind of also the preferred geometry in many laboratory experiments of rotating convection, what Hermann Klerks, for example, showed on Monday. And the main problem with liquid metal, of course, is that it's very hard to look inside a convection experiment. So, because we cannot do PIV or particle tracking or anything in there. So that's one of the motivations you want to couple to that. What geophysically relevant probably is that if we look, for example, one of the most recent dynamo simulations at the most extreme parameter of 10 to minus 7 done by Nat Schäfer. And what we see is that there's actually a huge difference between what's going on at in the polar region, so in the tangent cylinder essentially, and what's going on in the equatorial region. And the tangent cylinder essentially for Earth's core, which has a radius ratio of 0.35, has a nice aspect ratio of 1, which is kind of more coincidentally also the aspect ratio used in most laboratory experiments. Then we've also seen this nice Juno images. So this is on the south pole of Jupiter. Is it the north pole? I'm not sure. So both poles have nice, huge vortices. They are very different to what we see on Saturn. So that means the polar regions themselves are really interesting. And to quantify this a bit more, this whole connection between considering the sphere, the cylinder just as a subset of sphere. We've also done a simulation with magic and a spherical geometry. Here now in a thin shell, so not really Earth-like, for radius ratio of 0.8. And again, this is now the azimuthal velocity, and also here we see along the equatorial region we have strong zonal flows, while in the polar region we have more columnar convection. This is just simple Prandtl 1 case. Then we can consider our little cylindrical setup. It's kind of the subset up here, so tangent cylinder exactly would not work. And then we cut out some part of this cylinder, and we compared now with the cylindrical simulations that I've done with a fine volume code called Goldfish. And we see a nice agreement in the length scales and in the structures that we have there. And the main thing is, since I want to study liquid metal convection, is that if you want to study low Prandtl numbers, your resolution has to be much better than for a Prandtl 1 fluid, and which makes it very expensive. As I said, this is a very simple simulation with Prandtl 1, and yet you need much more grid points in a sphere than in a cylinder. So it's not really feasible to study that in any relevant parameter range. Well, it's actually also harder in the cylinder still. More recently, Thomas Agustin mainly did also a comparison again in a sphere with Prandtl 1, and he just averaged around 5% of the poles. So these are now these blue data points, and he compared it to direct numerical simulations from Stefan Stellmach. So these would be the orange symbols, and these are the Cartesian parallel periodic box, and also to the reduced model by Keith Julian. So these are the green symbols, and these agree very nicely, so that is also good. And for the problem with the cylinder, of course, is that our onset is not stationary like it happens in a periodic box, but that we have onset via wormholes. So actually our convection sets in much here, then we would still approach this kind of branch of the rapidly rotating convection. So which makes us rather confident that using this cylindrical model is still relevant for geophysical applications. And now I'm simplifying my system even further, so I'm not solving the full MHD equations, but instead I'm using the quasi-static approximation. So that means I'm looking at an external field and neglect all kind of small perturbations. I neglect them. I neglect the induced magnetic field due to the induced current. And that means my magnetic Reynolds number is really small, so smaller than 1. And this also means that my magnetic Prandtl number is identical to 0. And again, we could consider this either as a small local parcel in the polar region of a planetary core, and it's also good for our experiments. So to compare to experiments, our magnetic Reynolds numbers are really much smaller than 1. We lose some of kind of the relevant physics, so we have no possibility for magnetic overstability, and of course we cannot generate a dynamo or any dynamo action. But still we hope to get some insights through that for rotating Magneto convection, or for the fundamental physics. The good thing here is now that our current density is just described by Ohm's law, and the electric field can just be described by electrostatic potential. So this are now the equations that I'm going to solve with my final volume code. So these are just the normal incompressible Navier-Stokes equations. Here, that's the Lorentz force. And as I said, I don't have to solve the full induction equation, but instead I just solve a Poisson equation. And so this is really numerically much cheaper, doable. Then the most important control parameters, I think most of you know that, is just Rayleigh number, Prandtl, Rossby, the magnetic field, now Chandrasekhar number. And then this can also be combined to other numbers like Ekman number, which is more common. And what's important is the Althusser number, so which characterizes the importance between Coriolis and Lorentz force. Okay, so now we have a nice system. We think that it's geophysically relevant, especially for planetary core convection. And now we wondered, where should we actually do simulations? Where is the relevant physics happening? And of course, the first thing to do is linear stability and look at predictions. Here's one example for moderate Ekman number of 2 times 10 to minus 5. And that's kind of the standard picture people have of how convection occurs. So this is the critical Rayleigh number versus Althusser number. And then we would see, okay, for small Althusser numbers, rotation dominates, and we would have an onset through a geostrophic convection. And then around Althusser number of 1, suddenly magnetic field facilitate convection, and we have a minimum here, and the onset would be magnetic. Then, as I told you, we are actually having a liquid metal, so the Prandtl number is small, and then we can have an onset via oscillatory convection. And yet still for S around 1, it would still be magnetic. And if we go to core-like values of Ekman 10 to minus 15, again assuming a liquid metal, we'd still have our minimum for the critical Rayleigh number around Althusser 1. That's kind of the assumption for Earth's core, that Althusser is around 1, so everything should be magnetic. And one idea also here is that when we switch from stationary geostrophic onset to stationary magnetic onset, that's also connected to a change in wave number. So magnetic modes are usually expected to be much bigger than geostrophic modes that are rather small scale. So and then the naive assumption, or what you can read, is really, okay, since we are in Earth's core, we are here roughly, so we would expect large structures, which is kind of what's needed for dynamo action. And we now thought, so from rotating convection in a liquid metal, we have actually learned that this simple assumption that it's only the onset mode that matters is actually not quite true, but it actually we could extend probably these curves, and then we could see different critical Rayleigh numbers, and as soon as they would extend to this part, you would see a change in flow morphology, because we're not interested in the onset modes, but we actually want to go beyond that and to higher supercriticalities. So I looked just at the equation for the critical Rayleigh number by Chandra, and this is a stationary onset, so it's independent of the Prandtl number. Then we can rescale everything a bit with pi, and what you have to do is minimize it, and then this gives us a 7th order polynomial, which is of course not algebraically solvable. Numerically, it's absolutely not a problem. And what was shown, or what was actually first noticed by Donna Albert, is that a nice thing that only in a certain range, so of LSSR numbers, so this is now with increasing LSSR number, this is a very small LSSR numbers, usually just have one minimum, and then for a certain range, you could get several minima or 2 minima essentially. And she already predicted that we would have a coexistence range essentially where it would be possible to get magnetostrophic modes and geostrophic modes. So, and then again here on this side, the same is true still for planetary core values, so of the Ekman 10 to minus 5, so 15. So we would always have these 2 minima. And then if we look at the wave numbers, what one sees is that actually the structure is much more complex. It's not like, okay, there's one LSSR number, and then suddenly the geostrophic modes disappear. But instead, they extend further. Then this gray line is a maximum in the wave number. And then here we would have a magnetostrophic mode, and here it would continue to a magnetic branch. So what we see is the Rayleigh numbers where this could occur, they do not stop here, but actually they extend much further. So we can expect a much bigger coexistence range here. And then, okay, we cannot solve the 7th order polynomial, but we can make some simplifications, and then these are already well known, so we would have this geostrophic branch, and then of course rotating magnetoconvection behaves exactly like rotating convection. Then here in this branch we would get a magnetoconvection, so with the typical onset number, Rayleigh number of pi squared times Chandrasekhar number. Same is true for the magnetostrophic mode. In this case, you would assume that we have a fixed LSSR number, which then changes our 7th order polynomial. And if we say that now Chandrasekhar number goes to infinity, then of course we are only left with this term. And then we have purely magnetostrophic mode, which only depends on the LSSR number. And this was done by Altayeb in the 70s. And he then said, okay, essentially 3 regimes in rotating magnetoconvection, and this one is this switching parameter, so which would be the transition from geostrophic convection to magnetostrophic convection, which I showed you before. And then there would be also, of course, a transition from magnetostrophic to magnetoconvection. However, what we were interested in is what happens actually in this range here and here. And we can do this by doing the opposite limit, so still keeping LSSR fixed, and then going to the limit of Ekman goes to 0. And what we get then is also a nice 3rd order polynomial equation, which for once gives us then 3 roots, once describing the maximum, which goes with Chandra to 1/4. We also get this branch here of the magnetostrophic modes, which interestingly depends only on the Chandrasekhar number, not on the LSSR number. So even though we are in this magnetostrophic coexistence range, and this root is only real if the Chandrasekhar number is actually greater than 27 pi squared, which gives a lower limit for the magnetic modes. And I'm not really able to describe this one. Somehow I always lose this root when I go to a polynomial that's lower than 5th order. I don't know why, but at least numerically one can determine that the upper limit for this range would also go with Ekman number to the 1/3. So instead of 3 regimes that we would expect, we now end up with having 5 regimes. So one where we really just expect geostrophic modes. We have this coexistence range where we would expect, however, that the geostrophic modes dominate. Then this would be the fully magnetostrophic range, even though there are still some geostrophic modes. Then we have a magnetically dominated and yet magnetostrophic regime. And then only here we would have a magnetic range. So then we're looking at liquid metals. So again, we have oscillatory modes, but these are fairly simple and fairly straightforward to solve. And because we have a cylinder, we have also an onset via wall modes. And now, again, the same happens that we can either go through more the geostrophic direction, that it would behave similar to a Stewardson layer, and we can go to the magnetic branch, and then we would the wall modes behave more like Sherpa layers. Okay, that's now the summary for 2 × 10⁻⁵. This is what we would expect. So we see that there are different length scales for the onset modes, and the convection would onset actually here for low Althusser numbers via oscillatory convection, and for high Althusser numbers via wall mode convection, but not via magnetostrophic convection. And we then also could look at the Ekman dependence. Here, this is the critical wave number with Althusser. The Althusser range is now much bigger, and this is the critical Rayleigh number. So going up to Ekman numbers valid for planetary cores. And what we see is these regions become much smaller. So actually, we want to really go to small Ekman numbers so that we can really look at the different regimes. What I've done, however, is only look now at a small regime for relatively moderate Ekman numbers. And then did first a simple case where we just would expect oscillatory convection. And indeed, if we do that, our flow behaves exactly like normal rotating convection. We see these nice oscillatory columns. So this side will always be temperature, and this one will be a vertical velocity. So there's nothing new to see. Then we could also go to the other simple case, which would be the magnetically dominated regime. We would expect wall modes. And also here we see these retrograde drifting structures. What's kind of interesting is that unlike wall modes that we know from rotating convection, is that now, I hope you can see that, is that you have this nice uprolling of structures. Okay, now let's look at the more interesting case in the magnetostrophic coexistence regime. Where we would actually expect to now see these magneto modes if you have this naive picture of just having these large-scale structures. However, now actually all of these different modes should have kicked in. So the oscillatory modes, wall modes, magnetostrophic modes, and geostrophic modes. And then we can make some simple estimates how many structures we would actually expect to see in our cylinder by just using this estimate that one structure corresponds to half a wavelength. So for the wall modes, we would expect an azimuthal wave number of 4. Oscillatory modes should be around 13 structures in there. For the geostrophic modes, 29, so much more. And for the stationary magnetic modes, only 4 modes. So the expectation from many people would be we only have 4 structures because it's really the magnetostrophic mode that matters. However, that's clearly not the case. So the upper panel shows liquid metal convection, and the lower panel shows a comparison to Prandtl 1, so the standard case. So the first thing you probably notice is these are very different structures. So Prandtl 1 is probably not a good model for liquid metal convection. What you could also see is, so both movies are scaled with freefall time units. So liquid metal moves much faster, it's much higher Reynolds number than just the Prandtl 1, which just moves sluggishly around, has more these columnar structures, and it's clearly not the case for liquid metal. So clearly there is no obvious mode switching. We do not suddenly have just large scale structures. But now you could say, okay, I showed you before, geostrophic modes do still exist there. So what happens if we go here? Here they should stop to exist. So we only have the stationary magnetic modes, should still be 5 structures, oscillatory modes and wall modes. And for some reason, it's still not the case. We of course also have a lower supercriticality now. Again, Prandtl 1 and Prandtl 0.25 are very different. We now have also these nice, like rose petal-like shapes in the vertical velocity. Still, Prandtl 1 has not really changed. We still see our wall modes occurring here. If you do a rough estimate or roughly count the structures, you can come up with 17, so really the number we would expect from oscillatory convection. So clearly these modes seem to dominate. But of course, it's just some initial work. So, and here is now for the different regimes, going from geostrophically dominated magnetostrophic range to the fully magnetostrophic regime to the magnetically dominated magnetostrophic regime. There's clearly no change, no mode switching, or at least not obvious. So, and that's kind of also, so this is my first kind of initial work, but it already shows that still all the critical radial numbers are relevant. There's probably still in a liquid metal flow, we keep on having a strongly multimodal flow, even when we consider magnetic fields. And the aim for the future would be, of course, to characterize these different length scales, maybe with spatial DMD or POD. And it would, of course, be useful to go to more extreme parameters in terms of the aspect ratio, because there are not too many structures that fit into there in terms of magneto modes, but also to go to lower Ekman numbers, because then the scale separation would be much bigger. And then, of course, since we are interested in core convection, then there's often the question, is it actually compositional convection? So is it really true that we should care about low Prandtl numbers, or is it really more like Prandtl 1 behavior? And then eventually I want to also go to the full induction equation to also study the influence of the magnetic Prandtl number. And with that, I want to thank you for your attention.
So it looked like the comparisons that you've made were kind of at higher Rossby numbers. I mean, do you see a difference in modes at lower Rossby numbers? You're basically saying that you don't see the magnetostrophic mode, right?
I mean, of course, that's an issue because Prandtl number, since the Rossby number also depends on the Prandtl number, so it's much harder to go to low Rossby numbers in a liquid metal. But I mean, I've done that. So even for a Prandtl 1, I've done the same kind of comparison. Even then, the Rossby numbers go really much lower. Okay, so that should be right. And there we should actually be in the proper regime. And yet there's still no clear mode switching. Yeah.
What would you say your results?
Probably not.